Hello, this is question 5 of the Physics Paper 1 2019 exam. So in this question, we have a block that is slowly sliding down a ramp, and it goes from point A to point B, and there is friction. So the question says to us, an object of mass 1.8 kilograms slides down a rough curved track and passes point A, which is 1.5 meters above the ground at a speed of 0.95 meters per second. So the object starts here at 1.5 meters above the ground at point A, and at that point A is going 0.95 meters per second velocity. Okay, so the object reaches point B at the bottom of the track at a speed of 4 meters per second. Okay, so we can see over here it's rough, and then from C to B, it looks like it's not rough anymore. And we know that because the track is rough, it's going to have friction. And we have to take friction into account for all of our calculations. Okay, so it starts with the track at 1.5 meters off the ground and it ends at the bottom. Okay, so if we look up at our questions, the first question asks us to define the term conservative force. So we have conservative forces and we have non-conservative forces. A conservative force is a force for which the work done in a moving object between 2 points is independent of the path taken. Now, this blue part is what you have to write in order to get your 2 marks. If you don't have that underlined part, they will not give you your 2 marks. Okay. So a conservative force is a force for which the work done in a moving object between 2 points is independent of the path taken. Okay, so there are quite a few examples of conservative forces, but we'll go into that in the next question. And then obviously a non-conservative force is a force for which the work done in a moving object between 2 points is dependent on the path taken. So going on to 5.2, name the conservative force acting on the object. So examples of a conservative force are gravitational forces. Okay, so this is not the answer of this question. I'm going to write down the examples of conservative forces here. Gravitational force, elastic force in a spring, and electrostatic force. So it doesn't matter what path you take, if it's from really high to really low, or you on a wonky table or anything like that. These things, the work done in a moving object is independent. So it doesn't matter. The work done will be independent of what path you take. It doesn't matter what path you take, the work done did not depend on that. Okay. So now in our question, they're asking us what name a conservative force acting on this object. So we can't just name any one of the conservative forces that we know. We have to apply it to this question. So in this question, we don't have elastic force in the spring. We don't have a spring. We don't have electrostatic force. There's no electrostatics involved here, but we do have gravity. Gravity is involved. Gravity is pulling this block down towards the ground, and gravity is pulling it down the slope. And we have our different um parts of gravity. So we have the normal gravity, and then we have the perpendicular, and then we have the um parallel. Okay, but those are just different components. So the answer for this question our conservative our conservative force is gravity, so gravitational force. And these are just other examples of conservative forces. Okay, so our next question asks us, is mechanical energy conserved as the object slides from point A to point B? Choose from yes or no and give a reason for your answer. So is mechanical energy conserved? And do we have the same amount of energy at the top as we did at the bottom? And the answer is no. We do not have the same mechanical energy. We do not have the same mechanical energy at the bottom as we do at the top. Why? Because there is friction. And friction is taking away some of that mechanical energy. Okay. So the reason, no, there is friction, which is a non-conservative force, which means that when there is friction, mechanical energy is not conserved. So if there was a conservative force, for example, gravitational force, elastic force, um, or electrostatic force, and that was the only force that was acting, on it, then you would say yes, mechanical energy is conserved because only conservative forces are acting on the object. But we have non-conservative forces acting on this object, and our non-conservative force acting on it is friction. So no, there is friction, a non-conservative force doing work. Because friction is doing work on the system. Or you could say, no, the net work done by the non-conservative forces is not zero. Okay. So if the net work done by the non-conservative forces was zero, then we could say yes, this then mechanical energy is conserved. So if there was friction acting downwards, but then you were pulling it upwards at like exactly the same um, speed and there was no acceleration, then you could say yes, the the energy is conserved, but it's not because it's not zero. Okay. Question 5.4. Calculate the gravitational potential energy of the object when it was at point A. Okay. Now, what is gravitational potential energy? It is the energy that we have, the potential energy that we have because of an object's height above the ground. Okay. Gravitational potential energy, the potential energy that we have because of an object's height above the ground. Okay. The formula for gravitational potential energy is as follows. EP, which stands for gravitational potential energy, is equal to M, which is the mass, G, which is the gravitational pull, which is always 9.8 meters per second minus 2. And h, which is the height. M times g times h. M being the mass, g being gravitational force, which is always 9.8 meters per second minus 2, and h being the height above the ground that the object is. Okay, now all we need to find out is what is the mass of the object? We've got the gravitational pull, because that is 9.8, and then what is the height above the ground? So we're told that the mass of the object is 1.8 kilograms, and then the height above the ground we were shown here with this arrow, that it was 1.5 meters. We're going to go sub this into our equation nicely. EP equals 1.8 times 9.8 times 1.5. That, if you times that all out on your calculator nicely, comes to 26.46. Now, the question asked us for the gravitational potential energy, and energy is measured in joules, so joules is our unit. Don't forget out the unit, otherwise you will lose a mark. Okay, so that was question 5.4. Now question 5.5, let's read it nicely together. Okay, using energy principles, calculate the work done by friction on the object as it slides from point A to point B. Okay, using energy principles, calculate the work done by friction on the object as it slides from point A to point B. Okay, now the energy principle that I am going to use for this question is the work energy theorem. Okay, and the work energy theorem states, let me write this down. It's question 5.5. That the net work done on an object is equal to the change in the object's kinetic energy. Okay? So this is the theorem that I'm using. The work energy theorem, the net work done on an object is equal to the change in the object's kinetic energy. So we can see that we've got a change in the object's kinetic energy going from the top of the ramp to the bottom of the ramp. Okay, because it is slowing down. Oh no, it's going quicker. So the kinetic energy is changing. We've also got friction acting on it. The kinetic energy is going to change. We've got lots of stuff acting on it. So the kinetic energy is definitely going to change. Okay. And the formula that we get from this theorem is the net work done is equal to the change in the kinetic energy. Yeah. And the net work done for us is the work done by friction plus the work done by gravity. Those are the those are the forces acting on this object. Friction and gravity. Because gravity is pulling us down the slope by the parallel aspect of gravity. So gravity acts straight down. Gravity acts down the slope parallel to the slope and perpendicular to the slope. Okay, so this parallel gravity is what's pulling us down the slope, and then the only thing else acting is the friction up the slope. So those are the only things that can do work. Okay, work done by friction and work done by gravity. Okay, and we know that the change in kinetic energy is equal to half. Okay, we know that kinetic energy is equal to half mass times velocity squared. Therefore, the change in kinetic energy, is equal to half mv final squared minus half mv initial squared. So half of the mass times the final velocity squared minus half of the mass times the initial velocity squared. Change in something is always the final minus initial. Okay, always final minus initial. Okay, so now we have our lovely formula that we are going to use. Okay, we write this out better. Work done by friction plus work done by gravity is equal to half mv final half mv initial. Okay, don't forget the squares on the top there. Otherwise, you're going to get it wrong. Okay, the work done by friction, which is what we're looking for. That's what we're looking for. Plus, we've already worked out the work done by gravity. Gravitational potential energy is the work done by gravity. Okay, and we said that was 26.46 joules. Times 1.8 squared. Okay, the final velocity. You can see here the final velocity is 4, the initial velocity is 0.95. Okay, so this was the final velocity, which I said was 4, and the initial velocity is going to be 0.95. Okay, now if we type this to our calculator now, again. 13.4 minus 0.81 equals WF, that's 26.46. And then we go 14.4 minus 0.81 is 13.59. Therefore, the work done by friction is 13.59 minus 26.46. That gives us an answer of 12.87, and it's work done by friction. Work is measured in joules. Oh, sorry, negative 12.86. It's work done by friction, and work is measured in joules. This is our final answer. You may be wondering why there is a negative. How can we have negative work? So it is negative because it's the work done by friction, and friction is always acting against the motion. So it's technically like doing negative work, basically. So the friction is acting up the slope, like we said, and gravity is acting down the slope, and the the whole of the work together is acting down the slope because it actually goes down the slope. So if friction was more than the gravitational pull down the slope, then friction would be positive and gravity would be negative. But friction is acting down the slope now. Friction is acting up the slope down, but everything is moving down the slope. So friction, the work done by friction is negative. Okay, and then the last question of question 5 asks us, so it says surface BC in the diagram above is frictionless. Okay, so there's no friction, so there's nothing acting up the slope here. All of our work is going to be going down the slope. What is the value of the net work done on the object as it slides from point B to point C? Okay, um, so in the previous question, we said that the network, okay, this is not part of the answer. The network was the work done by friction plus the work done by gravity. Correct. Okay. But now, when we're passing from point B to point C, we are on the ground. So there is no work done by gravity. And we also don't have any friction because it's a frictionless surface. So we also don't have any work done by friction. Okay. So the work done by friction, there is no work because it's frictionless. And there's also no work by gravity because it's on the ground the whole time. Okay, so the net work when we are traveling from point B to point C is zero. 0 joules because that's work, or you can say zero. And we need an explanation for this. Okay, no, we actually don't need an explanation for this, but the explanation that they give in the memo is frictionless surface. There are no forces acting on it, on the block. There is no gravity. Or friction or tension, etc. Okay, so no work has been done on this block when it slides from point B to point C. It's just going to carry on for as long as it can because there's no friction holding it back. And there's also no gravity that's going to make it go quicker, or no friction that's going to make it go slower. So there is, in fact, no work being done. Okay, so that is it from question 5. Just something important to remember is the work energy theorem. It can come very much in handy. There are different ways to work out the network. You might have to use some trigonometry with if they ever give you the angle of the slope, if it's a slope like that. Obviously you can work out the angle if it's a like ramp type of a curved track. There we go. Um and yeah, just remember your components of gravity and draw a free body diagram if need be. Free body diagrams can really help. As you can see, I drew one over here. You can go back to my question 2 video if you would like to go over how to draw a free body diagram because I drew two there. But for now, this was question 5, and I'll see you in the next question.